I'm Pat Courtney with JTech, and today we're going to learn about bearing basics, which is basically an overview of the different types of rolling element bearings or anti-friction bearings. So we're going to find out what the functions of a rolling element bearing are, what they are, what kind of steels are used in rolling element bearings, and what the most important characteristics of a rolling element bearing are. So to start out with, we're going to, instead of talking about anti-friction bearings, we're going to talk about friction bearings. And so a friction bearing is like a bushing. So think of a wagon wheel, for instance, where you have a metal sleeve inside of that frame, and then you have a metal sleeve on that axle. And there's nothing in between there other than grease or animal fat, and that metal sleeve is acting as a bushing. And the key word here is sliding. So what you have is sliding motion. So you have two pieces of material sliding against each other. Now, and again, a friction bearing or a bushing can be made out of bronze or plastic. What we're going to be talking about are anti-friction bearings. So when we look at anti-friction bearings, we introduce a rolling element, whether that rolling element be a roller or a ball or a needle. So we put a rolling element into that equation, and then that reduces the amount of friction. So again, a great example, if we have this book and we try pushing it across the table, you're going to see that this is sliding, and it creates a lot of friction because of the amount of surface contact that the book has with the table. But if I take a rolling element and I put that underneath the book, now I can roll that book very easily. And so what we do is we introduce this rolling element to reduce the amount of surface contact, and we introduce rolling motion. So with those two together, it reduces the amount of friction or energy to rotate an object. So when we talk about rolling element bearings or anti-friction bearings, we talk about the fact that they're going to have a rolling element in them. But what's supporting that rolling element? What are the other components? Well, using a ball bearing is a great example. So most bearings are going to have what we call this outer race. In the case of a tapered roller bearing, and we'll get into more detail when we talk about the individual bearings, we call that a cup, but in most bearings, this is called the outer race. And then this section that's on the inside, we call an inner race. And then it's going to have your rolling elements. And a lot of times it's going to have a cage. So you can see that there's a cage that separates the rolling elements inside there. Now, when we go through these different types of bearings, sometimes they won't have a cage, and we call that full complement. And sometimes it won't have an inner ring. So the rolling elements will actually ride directly right on the shaft. So the rolling elements will ride right on the shaft material. But it's important to recognize what those different, when we talk about inner ring, outer ring, cage, those are the main components of any type of anti-friction rolling bearing. So another function of a bearing, of an anti-friction bearing, is to support the load of the device. So again, using the car example, you have the weight of that vehicle. It's going to be on the bearings actually in those axles are going to be supporting the weight of the vehicle and everything inside of it. What we do is we actually transfer the power from that engine to the wheels, and we do it efficiently. And the way we do it efficiently is by having those bearings that reduces the friction once that energy gets down to the wheels. So again, when we talk about load, we look at two different types of load. We talk about radial load, which is perpendicular to the shaft. So this would be a shaft or an axle. So a radial load would be perpendicular. In the example of a car, it's the weight of the vehicle. So it's gravity pushing down, and it's 90 degrees to the shaft. Now the other type of load we call an axial or thrust load. Now that's if we want to push the shaft parallel, or we want to push that sideways. Again, if the car were just going straight down the road, all those bearings would see would be a radial load. But now let's say we go around a turn. Well, when we go around a turn, that's going to want to push the shaft off to the side. That's going to put what we call a thrust load on the bearing. Now all the bearings that we talk about, all anti-friction bearings, are designed to carry either one of those loads or both of those loads. So one or the other. So it's going to carry an axial load, a radial load, or it might carry both an axial and a radial load. So now how do we define those loads within a bearing? Well, we have things called load ratings. So in every catalog for every bearing, there's a load rating for each bearing type, for each bearing. So for all bearings, you're going to have what's called a dynamic load rating and a static load rating. The dynamic load rating is what we use to calculate fatigue life. And so how long is that bearing supposed to last? So how long is that bearing supposed to last in your hub, for instance, in your car? So, well, that dynamic load rating gives us an indication of how much load that bearing can take and how many times it can rotate. So when we see a dynamic load rating, it's going to be just a number. It's going to be a weight or a kilogram. So it's going to be 5,000 pounds or 5,000 kilograms. So that 5,000 pounds is telling us how many times. It's telling us that we can put 5,000 pounds of weight on this bearing and we can rotate it 1 million times before it starts to fail, before it starts to fatigue. And so what is fatigue? Fatigue is when the metal starts to actually flake apart. So that's when the steel wears out. A great example of that is going to be a paper clip. So when you take a paper clip and you bend it enough times, you fatigue the metal and the metal breaks. It's the same within a bearing. So instead of bending it, we're rotating it. So we can get 1 million revolutions under that dynamic load rating before that bearing will start to flake apart. And that gives us an indication of how long, what size bearing we should use. That dynamic capacity is going to tell that design engineer what size bearing and what type of bearing that they need in a specific application. Now, the second type of load rating is called a static load rating. Now, static load rating is completely different than dynamic. They're not connected whatsoever. The dynamic load rating is the amount of force it takes to push that rolling element into the race and leave a dent. So how much impact does it take in a static situation? How much force does it take to push that roller into the race and actually leave a permanent deformation? Now, the problem with that permanent deformation is once that roller keeps going over it or that ball keeps going over it, then the bearing will fail. So that examples of that, where do you see that type of impact? You're going to see it if you drop the bearing, if you hammer it when you're installing it. But both of those load ratings are always found in the catalog. And it doesn't matter whose catalog it is, every bearing manufacturer is going to have those static and dynamic load ratings because that's what the design engineer uses to design that bearing into that application. Now, the next important function of a bearing is the precision. So higher precision allows higher limiting speeds, better accuracy of what the rotating device is doing. So think of precision as better circles. So the more precise that we make these circles, the faster we can go. Again, I'll use the car example. If you have tires and they're not quite round, what's that going to feel like? You're going to bounce around inside that car. Okay, but the more round your tires are, the faster you can go. Another great example is a dentist drill. Everybody hopefully hasn't had to have fillings put in, but that dentist drill actually has 2 little tiny bearings on it. So what happens if those bearings weren't very precise? Well, the end of that drill, the end of that shaft is going to be wobbling all over the place. So that dentist is not going to be able to make a very precise hole in your mouth. So you want really, the precision of those bearings is what controls the end of that shaft and basically controls that rotating device, okay? The last function of the bearing is usually the least obvious, and that's for the bearing to wear out. So the bearing tends to be where the wear occurs inside that device. It's usually the least expensive to replace. It's usually the easiest to replace. And it's also the critical component. So again, when a design engineer looks at, when they're designing an application, when they're designing a device, they're going to look at the life of that bearing, which is really going to determine the life of that device, or when that scheduled maintenance needs to occur. So again, if we look at your car again for an example, they're going to know that those bearings and those wheels are going to fail after 100,000 miles, or in your transmission after 200,000 miles. We can replace those bearings and we don't have to replace the entire car. And the wheel bearings, for instance, we can replace those wheel bearings and we don't have to replace the expensive axle or the frame that they're in. Now, one of the important things for all bearings is the type of steel that we use. So how do we get a precise, how do we carry that load? How do we carry the load? How do we go the speeds that we go? Well, we have to use a material that can handle that load, that high load. So the most popular steel that we use is called 52100. Now 52100 steel is a high chromium, high carbon steel. So 52100 steel is used in all rolling elements in all bearings. So if we look at a ball bearing, a spherical, a needle bearing, all of those rolling elements are going to use that 52100 steel. Now all of your ball and roller product, so again, spherical roller bearings, cylindrical roller bearings, tapered roller bearings, ball bearings, all of those, the races, so this part that's on the outside, the inside, those are all going to use 52100. The only exception to that is on a tapered roller bearing, on an inch-type tapered roller bearing. An inch-type tapered roller bearings could use a different type of steel, and we'll talk about that in a little bit. So why do we use 52100? Because it's easy to machine and grind. So what I mean by that is, you can tell by the surface of this bearing that how shiny it is. Well, that means that this bearing has been ground. If it's only been machined, it would still look kind of rough, but we need to make this surface very smooth. And again, I'll use the example of a car. How can you go faster on a gravel road or on a paved road? Obviously, you can go much faster on a paved road. So we want a very nice, smooth surface for those rolling elements to ride on. The other thing, it's got to be very hard. So it's got high carbon. So putting more carbon into the bearing allows that surface to be extremely hard. So how hard is 52100? Well, if I were to take let's say this is a file, like a metal file that you use to file things. If I were to try to file the outside of this bearing, I would actually break the teeth off the file. So bearing steel is considered one of the hardest bearing steels out there. In fact, a lot of knife manufacturers use it. It's extremely very hard. Now, the other type of steel is what we call 8620 steel. Now, like I said earlier, this is only going to be on inch tapered roller bearings, and it's basically in the United States. What's the advantage of the 8620? How is it different than 52100? Well, 8620 is a low carbon steel, but what we do is when we heat treat it, we introduce carbon to the outside to make it hard. Now again, this is very important because we need that same hard surface for those rolling elements to ride on. So why do we use that low carbon steel? Because then it keeps the inside of the bearing soft, and then it makes it more resilient to through fracture, to impacts. So think of a skid steer riding into and slamming into a stump, for instance. So there's going to be a huge impact on those axle bearings. So if you use a through hardened material, it's hard all the way through. We call it through hardened, and that might fracture because of that high impact. The 8620 has that softer core, so it's more likely just to dent, but it won't fracture the bearing completely all the way through. Now again, the bearing would probably still be damaged, but you wouldn't have that catastrophic failure from that sudden impact. So there's two other types of steel that we're going to talk about. One is a low carbon steel that we use for draw and cut product. And the draw and cut product, what we do on that, it's the steel that, well, we draw the product, so it's not machined or ground. So this draw and cut is the material is actually stretched. So we take a flat sheet of steel and we push down with a die, and we actually stretch the steel, so we're actually changing the thickness of the steel. So we're actually making it thinner as we stretch it. So we need a low carbon steel so we don't tear the material. If we have too much carbon in the material, then it will tear the material, and we're not able to form the cup. Now, how do we get it hard? The same way we do 8620. So we put it through heat treat, we put it in a carbon atmosphere, and we introduce carbon into the bearing, into the race, and that hardens that surface. Now, the last type of steel is what we call 1074 material. And 1074 material is what we use for our thrust washers and our thrust bearings. So a thrust bearing looks something like this. And so that thrust bearing is going to have a washer that it rides on. And these washers are usually, they're a 1074 material. Now these are a carbon steel, but they're not as high carbon as 52100. And the reason is because we can't have the 52100 because we stamp these. And again, too much carbon and the part will break when we stamp it. We form these races a lot of times, so we'll actually curve these. So to be able to form them and curve them, we need a lower carbon type steel in that. Now again, do we harden these? Yes, so afterwards These are going to be just as hard. All surfaces are going to have that Rockwell 60 is what we call. It's going to have that same hardness for those rolling elements to ride on. In summary, these bearings need to be very hard. They need to be very smooth. So the surfaces need to be very smooth. They need to be very precise. And they have to be inexpensive. So when we look at the types of materials that we use, but we have to have a hard surface. It has to be smooth, so we have to be able to grind it, or when we draw it, it can maintain that surface finish. Okay, so it has to have those characteristics. Okay, so what are the important characteristics of the different bearing types? So again, we're looking at these different bearing types, all these different types of rolling amounts. It's going to be the type and the amount of load that bearing can take. Obviously, the rolling element type, how fast that bearing can go, how precise that bearing can be, and then, of course, most importantly, in some cases, is the cost to manufacture, how much that bearing is going to cost. So that bearing type is going to have to be able to take either a radial load or an axial load, or both. The other characteristic is the rolling element type. So we can look at that bearing as to be defined by the rolling element, right, and the type of load that it carries. A good example is a spherical roller bearing. So this has got a spherical shape to it. We call this a spherical. This goes into a spherical roller bearing. Ball bearing goes into a ball bearing. Needle thrust bearing, again, needle thrust. So we're talking about the type of rolling element and then the type of load that it carries. Now what's critical, just about as well as the rolling type, right, and the type of load it carries, what's also important is the internal geometry of that bearing. So how the structure of those races, those inner races and outer races, what that structure is that carries that rolling element is also very critical to the type of load and how much load that bearing can carry. So when we talk about load or the type of rolling element, what's also important about the type of rolling element, it's not just the type, but then how big that rolling element is. So the size and how many of those rolling elements are really going to determine how much load that bearing can take. Now the next important thing is speed. So how fast can that bearing go? So all bearings have a limiting speed. They have a maximum speed. Again, if we look at the catalog, every bearing that's listed, regardless of manufacturer, is going to have a limiting speed. So what limits the speed of that bearing? Well, again, gets back to the rolling element type and the size. So ball bearings are typically going to have a higher speed rating. Why is that? Well, because when we put this on the surface, it's only contacting in this little spot. So remember when we talked about anti-friction bearings and reducing the amount of surface contact? Well, this ball is going to have a lot less surface contact than, let's say, a roller. A roller is going to have what we call line contact. So typically ball bearings can go faster. Now what's also critical, obviously, is the size of the bearing, size of the rolling element, not just the size of the bearing. We could have a very large bearing but with very small rolling elements, which means that bearing could probably still go very fast because, again, it gets back to the amount of surface contact. A smaller ball is going to have less contact than a larger ball. So these larger balls can't go as fast. So it's the size of the rolling element and the type of rolling element. In summary, again, the bigger the bearing, the lower the limiting speed. Now, what else limits the speed? Whether or not you use oil or grease. So again, oil is less viscous than grease, so you can obviously go much faster if you're using oil than grease. So what is the difference between oil and grease? Well, grease is just basically oil with a thickener added to it, usually a soap. So we add soap to it, and what does that do? It keeps the oil inside the bearing. So if we're using a shielded bearing or a sealed bearing, how does that oil stay in the bearing? If we just put oil in here, it would just come out through underneath the shield or underneath the seal. So we mix it with a soap, a thickener, and that thickener keeps that oil inside the bearing. Now the problem with it, though, is it's thick. So think of if you're running through water or running through Jell-O, which one's going to be easier to run through? Well, obviously water, because it's less viscous and it doesn't create as much heat when you go through it. So that thickener really adds heat to the equation. Grease also traps heat inside the bearing. And again, there's going to be different limiting speeds on whether or not you're using grease or oil. They're listed in the catalog. Now, what also controls the limiting speed is whether or not the bearing is sealed, shielded, or open. And what I mean by that is a seal is like this bearing here. So it has this rubber seal that's in contact with the inner ring. Now, an open bearing, when we refer to that, doesn't have any kind of enclosure. So a sealed bearing, because of that seal drag, so that rubber rubbing on that inner surface will actually limit the amount of speed that this bearing can go. So how much does it limit it? About 40%. So an open bearing of the same size, same shape, everything, is going to be able to go about 40% faster than a sealed bearing. Now, some people mistake the shielded product. The shield doesn't actually have any contact, so a shielded product would be able to go just as fast as an open bearing. Now, again, the seals don't play into a lot of the bearings because really the deep groove ball bearing is one of the only bearings that's sealed. There's a few needle bearing sizes that have, needle bearing types that have seals, but overall, all of your ball and roller product, the only one that's actually sealed is going to be your deep groove ball bearings. So another thing that affects the speed of the bearing is the precision level. So again, the more precise it is, again, the more perfect those circles. So when we look at this bearing, if we have more perfect circles and we keep this cross section, we call that the run out. If we're able to keep that consistent all the way around, the very same thickness on the inner ring and the outer ring, that allows us to go much faster. Again, I'll use the tire example. If we have very round tires, we're going to be able to go much faster than if they're slightly out of round. You're going to start bouncing around. And that's what happens when you start going super high speeds. Things start to vibrate, and that creates a lot more heat. The better surface finish, obviously, when we talk about precision, the smoother the surface, it's the gravel road versus the paved road. Obviously, the more smooth the surface, the faster we can go. Bearings are also classified by their precision level. And so when we talk about precision level, what do we mean? Well, that's basically how we hold the tolerances of the bearing. So when we make a bearing, and again, we'll use the example of the ball bearing, we're going to make this OD, or we're going to make this bore to a certain number. So let's say we make the bore of this bearing to 50 millimeters. Well, we're not going to make it exactly 50 millimeters. We're going to make it 50.000 millimeters to 50.010 millimeters. Okay, so that's really important. So that 0.010 is the tolerance. So the tighter that tolerance, the higher the precision. So, but when we look at a bearing, we're not just talking about the bore, the OD, and the width. We're talking about the precision of the balls. We're talking about the precision of how smooth the races are. And again, we're talking about that cross-section, being able to hold that cross-section consistent all the way around on the inner ring and the outer ring. So again, the more precise those circles are, the less wobble we get, right? So, and again, what's that going to affect? It's going to affect our speed, but then it's also going to affect how much that shaft is going to move. So typically we're going to have two bearings on here, and the end of that shaft is going to be doing something. That could be that dentist drill, that could be your wheel on your axle, that could be a CNC machine, but it's going to be, we want to control how much that wobbles. And the more precise that bearing is, the more precise the end of that shaft is going to move. And that becomes extremely critical when we're trying to machine or grind precision things. So a housing bore or a cast iron engine block, we want to make sure that hole is very precise. Well, that hole that we're drilling or machining can only be as precise as the bearings. So the last most important thing, I won't say the most important thing, but a very critical, is the cost of the bearing. So how much do these bearings cost? Which ones are the least expensive? Again, when we look at bearings overall, deep groove ball bearings tend to be the lowest cost. Probably with the drawn cup needle roller bearing as well. And so why is the deep groove ball bearing the lowest cost? Because they're the most popular bearing. So when we look at the entire bearing market, about 50% of the market is going to be deep groove ball bearings when we look at all bearings in general. So because these are so high volume and there's so much competition, the price is usually very low relative to the other bearings. The other is the drawn cut needle roller bearing. And why is this? Well, because one, there's not much material, and two, this is made on a high-speed press. So we're going to make thousands of these in an hour, so we can keep the cost down significantly, and again, because there's not much material. Now, the next lowest cost one, surprisingly, is going to be your tapered roller bearing. And again, this gets back to how popular they are and the volume of product that's made. So the tapered roller bearing is going to be your second most popular type bearing that's out there. And again, it's because of its popularity, its volume, these smaller sizes, and when I say smaller, about this size or bigger, are going to be high volume, and they're going to have very low costs based on the amount of people that are making them, the competitors, right, and the volume that they're making it. Now, when we start to get to larger tapered roller bearings, so as they start to get bigger, and when we start talking about spherical roller bearings and cylindrical roller bearings, angular contact ball bearings, now we start getting to some of those larger bearings. Now, those aren't as popular, and so they're not going to have the volumes. They're going to be much higher priced than the other bearings that we just talked about. So, and another good rule of thumb is generally the larger the bearing, the more it costs. There are exceptions to that, but again, as you get bigger, because there's more material, it's going to cost more. The other big cost factor is the precision level. So as we're trying to tighten the tolerances on that bearing, the price of that bearing will go up significantly. To give you just a good example, so this bearing by itself might cost $20 and just your standard precision. If we were to go to the highest precision level, this $20 bearing might cost $400. So you're talking about a factor of 20. So that precision level will dramatically affect the price of the bearing. In summary, rolling element bearings are characterized by the type and amount of load they carry, right? So the rolling element type, of course, how fast it can go, the precision level, and how much they cost. Bearings may seem simple, but they're at the core of motion in machines across every industry. From reducing friction to supporting loads, understanding the basics is the first step to mastering performance. Keep rolling forward, because now you've got the fundamentals to build on. Stay tuned for more bearing training from J-Tech, formerly known as Koyo.